This is John Black, Superchemist. I'm here to talk about orbitals today. But before we do that, you need to know what a shell is, okay? Now, shell is just the distance that the electron is from the nucleus, okay? Remember, the nucleus has the protons and the neutrons. They're all smashed up in the middle, right? And then the electrons, and even though it's not right, and most teachers would punch me for saying it, you can, if you want, think of it as orbiting the nucleus, the electron. But it really doesn't. If it did, you would have orbital decay and it would spiral into the nucleus over time. So I wanted to clear that up. But a shell, I want you to think of it as a floor number, okay? Like if you're in a tree, let's say a floor is 8 to 10 feet, right? And you jumped out of a tree, and I'm like, well, how many stories was it? How many stories you jump? And it was 20 feet. You're like, I jumped 2 stories, 2 floors. I was like 2 floors up. You're not actually in a house where you're on floors. You're in a tree. Well, I want you to think of the nucleus as the Earth, and just think of distance. Don't, pretend there's a building there, right? And every so often, that there's a floor. There's no in between. There's just one, floor 1, floor 2, floor 3. And that's basically what your shell is. Shell 1 would be the closest floor to the nucleus, you know what I mean? Shell 2 would be the next floor, and shell 3 would be the next floor. You're further and further away from the nucleus, which means there's not as much attraction. Instead of gravity, I guess you'd call it Coulomb force. But the further away you are from the atom, the freer that electron is. That's what a shell is. Now, what's an orbital? Now, keep in mind, an orbital is not an orbital. It's like meat and meat, you know what I mean? Just because they sound the same don't mean they're the same thing. One is meeting someone and one is eating meat. You know what I mean? Orbital has nothing to do with orbiting something. Okay, it just happens to be called orbital, probably because Neil Bohr's, man. That was the first guess on what was going on. Okay, but we know that isn't true. An orbital is just a volume of space. Okay, that's all it is. A volume of space around the nucleus where it's the highest probability of finding an electron. It's like 90% sure it's going to be there. But it is possible, to be outside of that range. There's a 10% chance it could be a little bit off. All we care about is that the orbital is a volume of space where it's most likely to be, right? And there's different shapes, all right? There's a S shape, a P shape, D, F, and G. I didn't put G down because you ain't even going to get up to F, so it doesn't matter. The first shell has one s orbital. Each time you go to a new shell, you get more orbitals and more variety, okay? Now, what are these shapes? Right here, I got 1s, okay? Now, if you had hydrogen, remember how we said the proton tells you what element you have, right? So if you have 1 proton, then you have to have 1 electron for it to be, and we don't care about the neutrons, to be, neutral, you know what I mean? And not an ion. And in hydrogen, it does matter because there's never a neutron, almost never. So it's really just a proton and an electron. You can see I have the X, Y, and Z axis like in math. It's just to show you how small that is and where it is, okay? That's the first shell, and it has an S, right? Each one of these orbitals can hold 2 electrons, right? So that means the S1 can hold 2 electrons, the P can hold 6, the D can hold 10, and the F can hold 14. Because there's 1 S orbital, 3 P's, and 5 D's, and 7 F's. If they all can get 2 electrons, you just multiply. So this 1s can hold 2 electrons, right? So it only has 1 with hydrogen. If you move up on a periodical chart, you'll see the next one is helium, right? So that electron would go into there, and you'd have 2 electrons in there, 1s2, meaning first shell, s orbital, and there's 2 electrons in it. Now, once you get up to 3 electrons, like lithium, you got your 2, you still have your 2 electrons, even though you can't see it, because these are spheres, right? So this sphere encapsulates that red sphere, right? But it's still there, right? Just like the nucleus is still there. This second shell has the same as that, 2s. So you got lithium gets an electron, and if you get one more proton on an electron, then you have beryllium. Now you have p orbital has 3 orbitals. These two sides are actually the same orbital. Like the x-axis has, this is one thing. Y-axis, this is one thing. Z-axis, this is one orbital. Each one of these are one orbitals. Now, when you fill in the electrons on the p orbitals, you got to fill them up evenly. You can't just put 2 in the same one. You got to fill up each one individually, an x1, a y1, and a z1. And it doesn't matter, you can call them whatever you want. This can be z, this can be x, this can be y. As long as you have 3 of them, you know one goes in each one at a time. You can't put 2 in without having one in the other ones. So, once you get past beryllium, you would be up to boron, right? Boron, you got your same 2 electrons, 2 here, and then you got 1 p electron. And that would go on one of these, either one. You can pick any one.
The first thing I want you to notice is this helium. This helium should actually be right there in that spot right there. The only reason they put it over here is because the groups going up and down, the columns going up and down are called groups. And they have a lot of things in common when it comes to chemical reactions. And this column right here, this group, has its orbitals all filled up in that shell. And so they all have similar chemical reactions. Or horizontal row, these are called periods, okay? Up and down is groups, crossways are periods. But the first 3 periods coincide with the shells. So you can see this, if this helium was over here, you could see that's the first shell. The second shell is this. The third shell, fourth shell. That's where it gets weird with the fourth shell. This first 2 rows, remember how we said there's one s orbital and it can hold 2 electrons. You can see there's these first 2 rows, that's your s orbital. And there's 2 rows because there's 2 electrons. Over here, you can see there's 6. This is your p orbital. Now remember there's 3 p orbitals, but they can each hold 2 electrons. That's 6 electrons. That's why there's 6 here. Over here, this yellow part, that is your d orbital. Remember there's 5 d orbitals. Each one has 2 electrons, so there's 10 of them. 1, 2, 3, all the way up to 10. This bottom part is your f orbital. Remember there were 7 orbitals, 2 electrons, that means 14 total. Now this actually shoves up inside here. See how there's lines up there? Now we don't put it there because we'd have to extend the s orbital way over there, and it would be we'd need a giant piece of paper. So let's do an electron configuration of a couple of these atoms. Here you have 1s1. Why do we call it that? Because it's first shell, s orbital, and how many electrons? There's 1. So it's 1s1. Helium should be right here. So it would be 1s2. 1 for the first shell, s for the type of orbital, and 2 for 2 electrons. Okay? Now when you get to lithium, you're in a second shell. See, you're in a second row here. So you put your third electron in, but the first 2 are still in that 1s2 shell. And then you would have a 2s1, meaning 2 for the shell, s for the type of orbital, and 1 electron. Beryllium would be 1s2, because you still have that first shell, and then 2s2, because in the second shell you have an s orbital with 2 electrons. Now if you get a 5th electron, where is it going to go? It's going to start going and filling up the p orbitals. Now remember, you have to fill up 1 p orbital at a time until they're all filled up, and then you can start filling in the second electron to each p orbital. So this would fill in 2px1, this would go into the 2py, this would go into the 2pz, and then you would start again, 2px, 2py, 2pz. and then they would all be filled up. Now when you get to 11 electrons, now you're down to the third shell. And again, you're just going to do the same thing. You're going to add an electron to because these are the s orbitals. S orbital, you're going to add an s orbital, and then 6 p orbitals until you get up to argon. Now this is where things get weird, and I'm not going to go into it too much, but the d orbitals are really freaky. For one thing, these, even though you're on shell 4 here, these s orbitals are in shell 4, but these d orbitals are in shell 3. The reason why the d orbitals are on a lower floor or a lower shell is because look at these s orbitals. There's no space. These are spheres. There's nothing to go in between. But look at these p's. The p orbitals have these spaces, right? And the d orbitals kind of like shove themselves in there. That's why they're higher energy, because they have other electrons all around them, repelling them. So these are actually, even though they're a closer floor, they are higher energy than the 4s. So when you get to potassium, sure, it comes out great. You'd have 4s1, calcium would be 4s2, and this next one's, I think it's scandium, sc. Now this is where it gets weird. When you're talking about electron configuration, or the electrons that are on a neutral atom, then you can just say that you have one in your 3d orbital and you have 2 in your 4s orbital, okay? But the order of addition, the order that those electrons actually fill the orbitals is different, okay? This d orbital is closer. So let's say I took off 3 electrons off of here, and you went back to argon configuration, electron configuration. You still have the same amount of protons, so you're still scandium. You would have none of your 4s and none of your 3d orbitals filled, right? Because you're a positive 3. You're up here by argon. Now let's say I added in 1 electron to Sc. That electron does not start filling out the 4s. It immediately goes into the 3d orbital. Now if you have a +2 where you add another, a +1 where you add another electron, then it will start filling up the 4s orbital. So each time you move in, say, to titanium, you're going to have a 3d2, 3d3, and you will still have these 4s's, okay? But because this is closer, it's in a closer shell. So they actually do, even though they're closer, have higher energy than these 4s. And I'm going to go into that when I get into valence electrons. Okay. So when you do an electron configuration and you're down to the d orbitals, all these d orbitals are actually closer than what they should be. Remember how the periods coincide with the shells just at the beginning. But when you get down to 4, these are 4s, all these are 3d. Same over here. This is 4p, this is 5s, 5p, but in between, these are 4. You go down 1. Same with the f orbitals. When you get down here to 6 period, these are 6s, these are 6p, but the d's are 1 lower. They're 5d's. But what about the f's? The f's actually go down 2 more. So instead of saying 6f, you would be at 4f's. You'd have 6s, 4f, 5d, and 6p. So keep that in mind. Now there are about 20 of the d orbital elements that just go totally out of whack, and they're just strange. Chromium, copper, ruthenium, palladium's twice as bad, silver, but there's 20 of them that do not go into this order that I'm showing you.
Always remember, science is great.